Okay, in the previous parts we built up a whole lot of things. We figured out what the moment diagram was. We started talking about how to decompose and work with that moment diagram, but that wasn't sitting within the context of what we're actually going to do with the momentary calculation to find the two displacement quantities. We wanted to know what the maximum displacement was in the middle span of the beam, and we wanted to know what the displacement was out here at the tip of the cantilever. Right, so there's a lot of diagrams shown here. Well, really one diagram, but a lot of bits and pieces on here. And so let's stay focused on the following. Right, so this curved line represents our actual qualitative deflected shape, and that's what we're going to use to develop our strategy for the moment area method. Right, so what I chose to do, since it's a simply supported segment, was to take one of the supports and draw a tangent to the elastic deflected shape and go all the way across the structure until I either hit another support, a terminal point in the structure, or a hinge. In this case, I can go all the way from left to right without interacting with anything else other than the terminal points. And so that's this big dashed line that we got here. Ignore the little tiny dashed line. That's just the tangent back out here at point A. We'll use that later. Right? So with that big tangent, what that does for me is enable me to create a little right triangle over here at the support at A. It's critical that I do this at the support A because the undeflected position of the structure is the base of the triangle that we have. And then, of course, the tangent is a hypotenuse, and the tangential deviation, in which always goes from the tangent to the elastic deflected shape, is then the third side of this right triangle. Right? We don't care about what the hypotenuse length is. Alright, so here's the deal here. This little angle then can be calculated as opposite over adjacent. Right? And so the span distance is L here. I don't think I have that marked, so let's get that marked. Right? And so that theta B is going to be then equal to rise over run. It's really tangent of theta, but it's really small. TAB is really small. We'll use the second moment area theorem to calculate TA with respect to B. And but note, if I know theta B, then I can then come figure out what this big rise is over here. Again, it's a right triangle. That's the only portion I'm getting. Now, I don't really need to know theta B. It's just a similar triangle between these two, right? And so that's why you have the 1/3, because this is 30 foot in the middle and this is 10 foot out here. So this is L prime over the middle span length. And so this big distance here is just 1/3 of what this tangential deviation is. That's why you see calculate TAB. Then I'll calculate TC with respect to B. That's the tangential deviation at C with respect to a tangent drawn back at B. Right? And that's this whole distance from the tangent all the way down to the elastic deflected shape. Right? And all we have to do to find delta C is find the difference between what that value is and what this one is. And that's it. Now the thing is you don't know in advance which one's larger. Is this little piece of the right triangle larger than the tangential deviation? Don't know, don't care. I do the calculation, and then I figure out whether the end of the beam actually went up or whether it actually went down. If it went down, then TCB will be larger than what the other one is. Technically, one of them's positive and the other one's negative. Right? And of course, in both instances, you'll use the second moment area theorem, which is the first moment of the area under the M over EI diagram between the 2 points in question, taken about the point in question, which would be, in this case, for TCB out here. Right? Now, if we want to find the value of delta max in the midspan, the problem here is we don't know where that's located, and it is not at the middle. We have to figure out where the beam has a zero slope. Right? So that's why I've got in here the theta A calculation, because I can go do the same thing. TBA divided by L gives me the theta A, and then I can figure out, using the first moment area theorem, how much area I need to walk from A over to here to get to a zero slope. That's not going to be easy to calculate, and I did it this way as opposed to already working with theta B, because it's actually easier with theta A than theta B because of that moment diagram. Right? Because you're working with either this area over here at the left, or you got got to deal with this positive negative area business, and that's not going to be easy to work with. Now somebody out there is saying, well, I know where delta max is, it's where the moment is maximum. No, it is not. Not. This is not a symmetric situation. So you can't make that assumption. You'd only get maybe kind of close, but you would be wrong about where and how much the maximum deflection is. Right? So you got to be careful about that. It's not located, delta max is not at 13.33 feet. It'll be somewhere between there and, well, I'm not really sure where it's going to be. Somewhere there in the midpoint, maybe a little bit past to the midpoint. It's a little complicated, and we got to figure that out. That won't be easy to do, but that's what you have to do, is figure what's going on there. And then once you know where it's located, you can find the tangential deviation. That's that little piece there. And once you know the angle, then you can get the big height and subtract off the tangential deviation, and bam, you've got then delta max. Now note, when you compare all of these calculations to that which you find in the computer model, they should be identical. Not about the same, they should be absolutely identical, because the momentary method is not an approximation. It is absolute correct to the same theory that's being used in the computer model.